thank you for participating in the first of its kind night at the museum. I do want to kick things off by a thought experiment. Talk to your neighbor. Why should we teach about climate change? Real quick, just first few ideas, share them with your neighbor, and we'll bring it back together. Why should we teach about climate change? Have you seen the world lately? One answer, a good answer. Why else? Teachers, what do you think?
I mean, if we don't teach it, who is?
If you don't teach it, who's going
Fox
to?
News.
Exactly, yeah. And the role of misinformation will creep in. How about over here at the back, the outside? Go for it.
What is any, you have to know what's going on with the planet so we can do our best to protect it?
We have to know what's going on, make sensible choices, sort of like the reason why we teach about health in the human body, so we can make good choices for our long-term health. Yeah? But anyone else from back there?
We also said that we need to learn how to protect our planet and exactly what we're protecting.
Definitely. Protect the planet, how to protect it.
So they have the responsibility to save the world, we don't have to.
So to shift the responsibility from our generations to future generations for saving the world. That's tangential to the reason that I'm going to talk about in a second. It's not dissimilar. I threw this down at the end of the class that I taught in the fall. Did a word cloud of student responses. So they'd already taken the class, and this is what they came up with. Emissions, adaptation, so reducing emissions, think about adaptation, how we're going to cope with climate change. Sustainability was an important theme. Healthy future, healthy planet, and then fear, hope were some of the words that they talked about. But the analogy that I like to make about talking about climate change, teaching climate change, thinking about climate change is to what previous generations may have experienced with a project like building a castle or a cathedral, where it's a multi-generational effort. And the reason, going back to your point, Minaj, is that if we're thinking about future generations, okay, let's say we figure it out. Let's say your generation gets it right, and we really curb emissions, slow down climate change, reduce its impacts, have a much more sustainable, low emissions future by the 2050s, 2060s, and beyond. We avert the worst and most catastrophic effects of climate change. Even then, the next generation and the generation after that is going to have to maintain and preserve that knowledge and pass that knowledge forward about how to build a sustainable and habitable global energy economic system in a way that is analogous, in my mind, to working on a cathedral or a church, where these projects would take over 100 years, 200 years in some cases, to complete. And so it was one generation to the next generation to the next generation, passing on that knowledge of how to build these structures. We're trying to build something that is a multi-generational effort as well. All right, what is energy? Turn to your neighbor, give them your first word that comes to mind. I've got some good ones that I'll share. What is energy? What is it that we're talking about? We talk about energy. What is energy? First word, Lee. What is energy? What's that?
Motion.
Energy. It could be motion. It's present in motion. What up here?
Everything.
Everything is a good answer. It's one of my favorite answers. Is that what you guys had too?
Now we were like, ability to do work.
Ability to do work, that's certainly what energy is. Alex?
I guess it's like a measure of what's going on.
Yeah, it's a measure of what's available to make things happen. I mean, nothing happens without energy. Used to do work, can't be created or destroyed. There you go. Teacher's got it. It's everywhere and in everything. My favorite answer to this prompt was music. Energy is music. It's all music. I was like, yeah, that's a good answer. And then he got really serious, and he was like, no, but like the vibration of the atoms, it's music, it's harmonics, man. So, yeah, no, it's in everything, and it is everywhere. I'm sure the corrections folks in the crowd would say, well, 0 Kelvin. All right, so common forms of energy. I'm going to walk through the forms of energy that we think about when we think about energy. And the point of this first lecture, point of the first series of lectures, is to lay out a set of building blocks and vocabulary that we can use to build up a theory around climate change and climate science and what's happening today, and look at the connections, the linkages between climate and energy, and really see something that I think, Don, you had said which is that you can't talk about, or to talk about climate without talking about energy is like talking about
Lung cancer without talking about smoking.
talking about lung cancer without talking about smoking. The two are so intimately related. They've been related throughout the history of our planet, and that's really the first series of lectures gets into that. They're intimately related when we think about the future of the planet. So I'll come back to that slide, talk about the forms of energy. But to make this point more clear, to drive home the connection between climate and energy, we're going to do the thought experiment of imagining that you are traveling to Earth from a star that's a M dwarf, a few tens of thousands of light years away. And so you've been in like deep hibernation. You've been put in deep hibernation where you make this interstellar voyage. The AI systems in your control panel wake you up, they bring you out of deep hibernation, and you start observing our solar system from the edge of the solar system. And you look out and you see that the third rocky planet from the star has this pale blue glow to it. And because you understand something about energy balance, you can see how reflective the pale blue dot is. You can see how far it is from the star. You're able to calculate how much energy is going into it and how much energy is coming out of it. And because you can do this calculation, which we'll show in a subsequent lecture, you can easily determine that the surface of this planet, this pale blue dot, the third rocky little planet orbiting the star, should be completely frozen over. It should have no liquid water on the surface, just by its energy balance alone, just by how far it is from the star and how much sunlight it's reflecting. And yet that pale blue glow tells you that there are liquid oceans on the surface. And so maybe you turn to your colleague and say, there's liquid water on the surface. And your colleague says, but its energy balance suggests that it should be frozen over. And you conclude through this dialogue that it must have greenhouse gases in the atmosphere. The only way to reconcile the energy balance at the surface is to assume that it must have greenhouse gases trapping heat to keep the liquid oceans on the surface actually liquid and not solid. All right, next prompt here. What is climate? Start with the back. What do you guys come up with? First words.
You said it's the general pattern of weather over a certain amount of time.
General patterns of weather over time, so patterns over time. Teachers, same, patterns over time. Yep, long-term averages, yes.
It's an evidence-based prediction.
Evidence-based prediction, yeah. So you're looking at the past to make a prediction about what you should expect now. Anything else come up? I want to make a distinction we've made in class as well between planetary climate and local climate, and both are important when we think about climate change. These are the building blocks of like climate theory. Planetary climate is determined by the energy balance. So that's the amount of sunlight reaching the planet versus the amount of outgoing long-wave radiation and the amount of sunlight that's reflected. That's just for the whole globe. We don't know anything about what's expected at a particular spot. This is just the incoming versus outgoing energy. When we think about local climate, I'd like to use a now fictionalized example from my own life. So I'm going to say it's you, because when I talked to my family about the possibility that these lectures would be on YouTube, after the first round of them being on YouTube, they asked if I could please stop using the real retirement home where my own grandparents were, and stop using my actual aunt's real name in the lectures. So I haven't done that anymore. So we're going to pretend it's your aunt, or it's you. And it's your grandparents who have retired to Kendall, which is just on the other side of the lake. It's like directly across the lake from us. And we'll say this is what happened to you. Your grandparents got a dog. They didn't expect the dog to still be alive when they went into the retirement home. But it was very healthy when their health started to deteriorate. They got a home at Kendall, and they had to take the dog with them. And so you or your aunt goes their lunch break or your lunch break, and you pick up the dog from their apartment at the edge, the corner of Kendall down here, and you walk them the perimeter of the Kendall retirement community. And of course, you take the dog, and it has its own path, and it zigs and zags and swerves all over the place. It chases the squirrels, and it smells the smells, and it takes in everything. But your path is really smooth and steady. It's around the perimeter. And this is sort of like the difference between weather and climate. So your path, your aunt's path, is like climate. It's the steady transit around our star every year, same basic path, same trajectory around the star. But weather is what actually happens. Weather is the zigs and the zags, the variability that we experience from one year to the next. And so we talk about climate change, we're talking about climate, we're talking about expectation for a given location. And that's going back to the idea of averages, or a long-term expectation, or prediction based on long-term averages. It's based on weather, but it's just an intuition for what should be happening, what is normal at a given location, at a given place through time. We talk about climate change, we're of course talking about changes in those expectations. And what we're going to get into throughout this series is the connections between between climate and energy. So go ahead, make some connections right now in your groups, in your pairs. What are some connections between climate and energy? Connections. Alice and Lee. Connections between climate and energy.
It's the primary source of emissions.
Yes. So one connection is that our use of energy, our energy system today, which is 75–80% fossil fuel based, is changing the climate. That's a pretty important one. And if we think back on a paleoclimate timescale or geologic timescales, because we are here at the Museum of the Earth, those are fossil fuels, meaning they accumulated in times that were generally quite a bit warmer and had more CO2 in the atmosphere. And we are tapping into those energy reserves that have been stored underneath the surface of the Earth for millions of years, releasing them into the atmosphere, and bringing back climates that we haven't seen in tens of millions or hundreds of millions of years. And some of the creatures that you may see in this museum, which look quite foreign to us now, thrived during those much warmer climates with higher CO2. So another connection between climate and energy that I want to make is through radiant energy. We already hinted at this a little bit. Before we get into radiant energy, we've got to review two important principles of ordinary matter, which is that number one, it continuously and spontaneously emits electromagnetic radiation. What that means in just a second here. And we need to be aware that the kind of electromagnetic radiation emitted depends on the temperature of the object emitting. Right? So two facts that are important about electromagnetic radiation when we think about radiant energy. We're all emitting it. Every object in this room is emitting radiant energy, and the type of radiant energy that it's emitting depends on its temperature, all other things being equal. So this plays out in interesting ways for planetary climate. And before we get into that, just want to review different types of electromagnetic radiation and how they are connected to the temperatures that are characteristics of the objects emitting those different types of radiation. So the lowest frequencies of electromagnetic waves are radio waves, and they're emitted by very cold objects well below 0 Celsius. Somewhere in the middle, like us, you have infrared radiation. So if you can see us in the infrared, we would be glowing because we emit lots of infrared radiation because of our warm body temperatures. And as you move out to warmer and warmer objects in the universe, so stars like our sun or even hotter stars, we start to see emissions of ultraviolet radiation, X-rays, gamma rays. And this is important for the greenhouse effect to think about. I'll walk you through why. But first, I want you to imagine the experiment that some of you have seen live, but I'm not doing live in the museum tonight for fear of triggering the fire alarms or the sprinkler system. You took a blowtorch and a fork, right? Took a fork and a blowtorch, just held it for a few minutes. The tines of the fork would start to glow red. And the reason why they're glowing red is because they're hotter. And when they're hotter, they're emitting visible radiation. And you've probably seen this if you've seen lava or pictures of lava. The reason why lava glows is because it's relatively hot compared to the surface of the Earth, so it's emitting visible radiation. Now, when we look at the long-wave radiations, objects that emit long-wave radiation, like ourselves, or in this case, two buildings which are next to each other, you can see one of these buildings has better insulation than the other one. The one that's emitting more long-wave radiation has poorer insulation. It's leaking energy, it's leaking heat out into its environment, and you can see that in the infrared. The building on the right has better insulation and is containing that heat. It's trapping that heat more effectively inside it. Here's a picture of a steam engine in the infrared. It's not quite hot enough to be glowing in the visible wavelengths, but it's emitting a lot of infrared radiation. This is a picture of a snake wrapped around a man's hand. And humans being warm-blooded and snakes being cold-blooded means that you can see that difference in the infrared. Again, back to our thought experiment. You've come from some distant planet, you've just woken up. Maybe you're exploring Earth now, and your eyes evolved to see in the infrared. So you go to the reptile show at the, the nature center at the reptile show, and very clearly you can see that there's a big difference between the temperature of the snake and the temperature of the man's hand. It's also great, this is just free advice, when you're in a hurry and maybe your partner worried about what they're wearing, and they ask you how they look, and you can't really give, you don't want to give an honest answer because that would be hurtful. You just say, you look radiant, and it's scientifically accurate. It's a scientifically accurate way of handling that difficult situation because you got to get going. All right, here's a cat. Picture of a cat in the infrared. And as you probably know, cats tend to have thinner fur right in front of their ears, and that thinner fur lets out more infrared long-wave radiation. The thicker fur around the rest of the cat's body traps the heat close to its surface, or the skin surface, and keeps it warm. And that's a nice analogy, a nice segue to the greenhouse effect. Our planet is warmed up by a star, and it gets rid of radiation in the long wavelength, an infrared spectrum. This is a picture of the Earth in the infrared. This is from your spaceship, which can take pictures in the infrared. And what you can see as you close in on this third rocky planet orbiting the star is that at the high latitudes and in the polar regions, there's lots of clouds, and cloud tops are cold, and so they're emitting less long-wave radiation. They're trapping long-wave radiation closer to the surface. The subtropics and the desert regions of the planet are relatively clear, and those clear skies without any clouds let the radiation right back out into space more readily. Not as much is in the way. Then in the tropics, there's lots of clouds. And again, they're acting like the cat's fur. They're trapping heat close to the surface. And you get to another subtropical zone that's letting long-wave radiation back out. And then you're in the South Pole region, southern high latitudes. The clouds are cold, the climates are colder, they're emitting less long-wave radiation. Greenhouse gases act a lot like clouds, in the sense that they're able to trap or absorb long-wave radiation. And when they do that, the atmosphere warms. And the more greenhouse gases you put into the atmosphere, the more of that long-wave radiation they trap. And because they trap more long-wave radiation, you experience more warming. Quick recap. All ordinary matter emits EMR. The type of EMR emitted depends on the temperature of the object emitting it. The sun, by our standards, is very hot, so it emits a lot of shortwave radiation. The Earth is not as hot, so it emits long-wave radiation. And greenhouse gases, because of their molecular structure, are able to absorb that long-wave radiation. And when they do, they vibrate faster, they bump into their neighbors, and they warm the gas. They warm the atmosphere. Finally, energy, talked about, is something that can do work. Energy can't be created or destroyed. Planetary climate is determined by the balance of incoming shortwave radiation, outgoing long-wave radiation. Local climate is an expectation for the weather in a given location. And Climate change means we're talking about a change both in the expectation and the energy balance. On Earth, right now, there is an energy imbalance. Because of our fossil fuel emissions, we are trapping slightly more energy than is going back out to space. And that is warming the planet, it's warming the oceans. The oceans have a lot of mass, and they're taking a long time to equilibrate. So the warming that we're feeling now, the hottest summers that we're feeling, these heat waves that we're feeling, are really the effects of greenhouse gas emissions decades ago. Because the planet is still catching up with the CO2 that we've already put into the atmosphere as a function of this energy imbalance. It works out to something like, I think, about 0.5 watt per meter squared on average globally of energy imbalance. It's going into the climate system and causing it to warm. Just like if you plugged in a water boiler, you'd be putting more energy into that water boiler than it was emitting, and the water would warm. The same exact thing is happening to our planet. So in your observations from your spaceship, if you're looking at this planet that may or may not have intelligent life on it, it's still debatable. In your mind, thinking, I don't know how intelligent these species are. You're watching and you're saying, look, there's more. Not only does it have liquid oceans, not only is it habitable, there's more energy going into it than is coming back out. You would predict correctly that climate change would be happening on this planet. Knowing nothing about fossil fuels, knowing nothing about our global economic financial system, knowing nothing about our economy. You just say, well, there's more energy going in than is coming back out. It's got to warm. That's just physics. Like, we know physics pretty well. We traveled a small portion of the galaxy to get here. There's definitely going to be global warming on this planet. Like, I don't care what any news organization named after any animal says. There's definitely going to be warming. All right, and I'll end here with a picture that inspired the title of this presentation, pale blue dot picture, which was taken by the Voyager spacecraft as it left our solar system. Carl Sagan, famous Cornellian. I got to meet him once, actually. It was like meeting my hero. He signed a book, The Demon-Haunted World, for me when I was like 16 years old. It was amazing. My dad tried to make small talk with him, and it worked because Carl Sagan was just like so charismatic and charming. And he wrote this passage. I encourage everyone to look up and read. He talks about looking at this picture where there's just like a pixel of light. It's sunlight reflected by the Earth back out into the vastness of space. And he says, think about how everyone you've ever heard of, everyone you've ever known, everyone who's ever lived there in this tiny little mote of dust suspended in a sunbeam. And it underscored for him, and I think when I reflect on it, and I hope when you reflect on it, the importance of protecting this tiny fraction, a tiny, minuscule fraction of the solar system that we live on, even from ourselves. So we'll end there for this lecture.
Thank you. Thank you.
Encourage everyone to walk around, take your chairs with you, and set them up. You'll set them up right below us in front of where it says 4.5 billion years on this unique planet. There's a little sign down there. You put your chair down there, facing the 4.5 billion years, and then we will move the screens and the lights and the cameras, and we will resume with the next lecture, which is only about 12 minutes long, called Goldilocks and the Three Planets. Ready, set, go. About 15 minutes.
All right.